I want to show you a case study using HyperLith where we're going to look at 45 nanometer lines through pitch, and we're going to look at the focus shift at different pitches, and we'll look at the depth of focus, and we'll do this for various mask models. So we've got 45 nanometer lines through pitch for 3 different mask models: Kirchhoff, rigorous, constant scattering coefficients, and rigorous non-constant scattering coefficients. I'll explain what those are in a minute. ARF, C-quad illumination, immersion. The pitches from 130 to 400, and we'll anchor at a pitch of 200. And we'll apply biases for the rest of the pitches to make them print on target, and we'll do this for each different mask model. So the various mask models are attenuated PSM. Well, they're all attenuated PSM, but the first mask model is a Kirchhoff mask model. And in the Kirchhoff mask model, it's a binary thin mask model, and the transmission is either 1 or it's 6% with a pi phase shift. Then we have rigorous Tempest FDTD model, constant scattering coefficients. In constant scattering coefficients, we only simulate one angle of incidence, the normal wave. And in the rigorous non-constant scattering coefficients, we rigorously calculate the scattering coefficients for 4 angles. I'll show you this in the HyperLith right now. So I've done all these simulations, and I'm just going to go over the setup. Okay, so here is our these are the outputs, but I'll take you through. I have the Kirchhoff case loaded, so you can see the mask technology is a Kirchhoff mask technology. The mask pattern, I've done the the biasing through pitch, and I followed the procedure that I have shown in previous videos, where I simulate and then I apply the bias. I apply the simulated CDs in a bias here, but don't worry about that. Just assume that you could have imported this from GDS file that's already been corrected, or you already knew the biases from your mask or whatever. But in this case, for each different mask model that I used, I ran the bias through pitch operation so that all of the line prints on target for all of the pitches. Okay, so the stepper setup is C-quad illumination 0.9, 0.7, and a 1.35. I'm not using a resist model, which means that we'll just be basing our CD measurements by basing them on thresholding the aerial image. And because we are going to want to really look closely at process window size, I've put a lot of points here. So a lot of focus points and a lot of threshold points, plus or minus 100 nanometers depth of focus range, and plus or minus 20% threshold or dose range. So that's the Kirchhoff model. The other ones, let's look at the other mask models. Here is the constant scattering coefficients. And on the mask technology, I've just chosen our basic, the pre-configured DUV attenuated PSM mask technology. And just for the sake of comparing this constant scattering coefficients with the non-constant scattering coefficients, I'll customize it. And what you see is that with the constant scattering coefficients model, you simulate just the normally incident wave, and you calculate rigorously the scattering coefficients for this wave. But then you use those scattering coefficients for all of these source waves at the various poles. That's called constant scattering coefficients because we are assuming that the scattering coefficients are constant and the same for all the source waves. Let's compare this to the non-constant scattering coefficient setup. Give it a second to load. And in this situation, you have 4 angles of incidence that we rigorously calculate the scattering coefficients for. And now this is non-constant scattering coefficients because the source waves in this pole are using scattering coefficients calculated from this wave, whereas the source waves in this pole are using the scattering coefficients that were rigorously calculated for this wave, and so on. So we do not have constant scattering coefficients. They are changing. They are non-constant scattering coefficients. That's why we call it that. So anyways, let's get to the results. Again, for the various mask models, the patterns are the same except for the fact that the biases might be a little bit different. So in our results, we've got the Kirchhoff first, and we'll look at the we could look at the FEMS and process windows. Let's just look at that. We'll put these on separate plots just to give you an idea of what we're looking at. So we've got give it a second to generate this plot. Okay, so we've got Kirchhoff mask model. This is the process window for the pitch 130. Then we've got pitch 140, 150, and if I use the arrows, I can scroll through these. So you can see that the process window is moving around a little bit. It's moving up and down a little bit. They should kind of all be centered because we biased through pitch, but we didn't do that great of a job of biasing through pitch. So they're moving around, but that's not going to affect our depth of focus and our focus center that much. So as we go through these, you can see that the process window size and the depth of focus is changing for the different pitches. But that's not convenient to look at. We'll look at the actual, let's say, depth of focus. Okay, so here, give it a second to generate this plot now. It's going to plot the depth of focus for the various pitches. Okay, so here we've got 90 nanometer depth of focus, and then for this particular pitch, which looks like a 150, we have a very low depth of focus, and then we quickly move to a high depth of focus, and we get this repeating pattern here as the pitch increases. Okay, so we can look at those for all of the we can look at this for all of that data. Let's see, I think I have it saved here. Okay, so we could go through and make those plots for all of the 3 different models, mask models, but I've just got it loaded here, and then we can compare them quickly. So here, this is the depth of focus versus the pitch. And we see for, it's not labeled correctly, but I can label it. Let me just double click here and label it correctly. This is the Kirchhoff, and this is the constant scattering coefficients, and this is the non-constant scattering coefficients. Okay, so what we see is that something kind of interesting here. The Kirchhoff, which should be the least accurate, and the non-constant scattering coefficients, which should be the most accurate, agree better than the constant scattering coefficients. That's not that surprising, but it is a little bit interesting. It's just showing that the blue curve is closer to the black curve. So in this case, doing just a rigorous simulation at normal incidence is probably less accurate. Well, it is less accurate in terms of calculation of depth of focus than doing a full non-constant scattering coefficients, which should be the most accurate. Now, here's where now let's look at the center, the focus center. Now this is a little bit more interesting. Again, let me label this properly. So I'll call this the Kirchhoff. This is constant scattering coefficients, and this is non-constant scattering coefficients. So what we see here is that the Kirchhoff, it gives no focus shift for different pitches. And what we see is that the non-constant scattering coefficients, which should be the most accurate, gives some amount of focus shift, about 8 or 9 nanometers of focus shift, particularly for the lower pitches here. This is pitch 130, 140, 150, 160, 170, 180, up to about pitch 200, where you start getting constant focus shift. So this is the best focus position. It's the center of the ellipse when we look at the process window. Now for the constant scattering coefficients, which is less accurate than the non-constant scattering coefficients, for the constant, the red curve, you've got pretty crazy changing focus center here. Okay, so it's going from -20 up to 0, basically. So I'm not really sure what to conclude here. I'm just basically showing how the software can be used to make a prediction of focus shift through pitch. But out of curiosity, I wanted to look at a situation where I'm varying the thickness of the chrome, of the MOSI on the, right now it's 68, but I did a simulation where I varied the thickness and from I think 67 to 71. And let's look at those results. First, I didn't bias through pitch as for the different thicknesses. I just kept the bias for the thickness of 68. And you can see that the CD is moving around a little bit, but I don't think it's moving around enough to affect the actual process window. Here is a plot of the, I've already made the plot, I'm just bringing him up. This is the plot of the depth of focus versus the different thicknesses of the MOSI. And it's not changing. The depth of focus is not changing that much. But what is interesting is that the focus center is a function of that thickness of the MOSI. I mean, this is not a big change, right? This is from -2 to, well, -2 to like 0. So it's, 8 nanometers, 8, 9, or 10 nanometers for in the case of MOSI of 65. But you see that the amount of focus shift you get is less as the MOSI gets thicker. Now, we should probably extend the range here and really investigate what's going on. But again, the point is to demonstrate how the software can be used to do that. Let me just load that file just to show you how the setup looks. And this was all the data for this plot was obtained in one simulation. No scripting. You didn't have to go to Excel and organize the results. You can just do this all right from Panorama, right from HyperLith. So all I did was I took the non-constant scattering coefficients and I put a variable here for the chrome thickness or the MOSI thickness, and I let that variable go through several values. So again, we've investigated the focus shift versus pitch, and in this case it's for various thicknesses of MOSI. Okay?